Yes, I can do that. Should I do the introduction also in English? Or...
C'est comme tu veux pour l'introduction.
Alors, je la fais. Javier, I do it quickly, a short introduction in French, and then you can start the seminar, okay?
Okay.
Donc aujourd'hui, c'est Hector Hortua qui va nous faire un séminaire. Hector a fait sa thèse à l'université de Bogota en Colombie sur les champs magnétiques primordiaux, et il a ensuite fait un postdoc en Roumanie sur l'application de méthodes de machine learning pour l'inférence de paramètres cosmologiques, et c'est de ce sujet-là qui va nous parler aujourd'hui. Voilà, je pense que ça suffit, et on racontera des choses beaucoup plus intéressantes. So Hector, if you want to start, it's okay.
Okay, so thank you very much. Hello, everybody. So first of all, I want to thank you for inviting me to give this talk in this seminar. So today I'm going to talk about uncertainty quantification in deep learning and application in cosmology. So this is the outline of the talk. First, I want to discuss briefly the applications in deep learning. Then I will discuss the importance of including uncertainty in machine and deep learning methods. And after, I want to show you the different techniques that people already have in order to include uncertainty in deep learning methods. And also I describe the types of uncertainties that we find in deep learning. And then I will focus on Bayesian neural nets, which is one of these methods which allows to get or to compute these uncertainties. And finally, I will show you some applications in cosmology. Okay, so let's get started. So thanks to the increasing the technology, deep learning has become one of the most powerful techniques for which are used in different disciplines. And this is because this quality for solving inverse problems. So from deep learning, we have different applications, different technologies. So here in this slide, I show you one example from the image that you can see there. So this is my picture combined with Van Gogh painting style. So this is what is called the transfer style, and this is one of the techniques in computer vision. So computer vision is just to analyze the data in form of video or images. Also, we can use natural language processing for analyze data. From this, we can also create a poem. So we can create a translator. So or these chatbots, which is very very applied in the industry, and also we can use audio for speech recognition. Now, depending of so in deep learning, also we have different tasks, and one of these example is one of these tasks is reinforcement learning, and it basically is when you have the system and the idea is that the system interacts with the environment. Based on and the idea is that the machine tries to learn some rules in according to this interaction. And one of these applications is autonomous driving. Also, we have this unsupervised learning, which you have the data without any labels. So basically, the idea is that the machine tries to find some features, and depending on these features, it start to cluster the data according to the similarities. One of these applications is anomaly detection, which is very useful in medical recognition, for instance. And finally, we have this task, which is supervised learning, and it's when you have the data, and this data, you have the features and also the labels. So with these labels, allows to train the machine. And depending on the nature of the target, if it's a continuous variable, we have a regression, or if it is a discrete, we have classification. So here I want to use this couple of examples in order to motivate the inclusion of uncertainty in this kind of techniques. So let me start talking about the regression problem. So in the left panel, I show you an example that I did using the Quixote dataset. So this Quixote dataset consists in different boxes of any-body simulations, which each box was generated using a certain set of cosmological parameters. And then I use the machine learning, the deep learning methods in order to train the model and predict the parameter, the cosmological parameters for a specific box. So in this plot, you can you see the pointer, right?
Yes, we can.
Yes.
Yes.
Okay. So in this plot, I show you the x-axis corresponds to the true value of the sigma 8, one of these cosmological parameters, while the y-axis corresponds to the prediction given by the network. So in principle, you can see that the model of the machine is learning and can estimate the cosmological parameters. And here below, you can observe an example in the test set, which are data that has not been seen by the machine. And I just take one example, and you can observe that the value predicted by the network is around 0.8774, while the true value is 0.8578. So in principle, you can observe that the prediction is quite close. However, if we pass through another kind of simulation, so maybe the real data set in which we don't have the true value, this is actually what we want to get. In principle, we don't have any idea if how far or how close is the predicted value with respect to the true value. So in this case, we don't have enough information to trust on these predictions, for the reason that we need to include some kind of uncertainty in order to see how confident is the network with respect to this predicted value. So now I want to explain a little bit the classification. So in classification, since we have discrete values, it means that at the end of, or in the top of the neural network, we can add some activation function like a softmax. And basically, from this function, we get in the output of the network some probabilities. So the sum of all this output must be one, must be some one. And again, in this for this classification example, I use the NIST data set, which consists of a set of images, which has the handwriting numbers. So I trained this classifier, and at the end, I got 99% of accuracy. And after, you can also do this kind of plot with confusion matrix, in which you can get the accuracy, precision, recall, all these metrics that you can use in order to assess the performance of the machine. And then again, I pass through an image in the test set here, which you can see this image here. And the machine or the classifier predicts that this is the number one with a probability of 99.7%. So here for classification, now we have an addition, we can see an additional information. We don't have, we have not only the prediction value, which is one, but also we have another value which corresponds to the probability that this value is, that this image is equal to one. And in this case, so now we have an additional information. So in this case, now we can say that we can be confident about this prediction. But I mean, some people sometimes confuse maybe this or can associate this probability with uncertainty, with the uncertainty that the machine has with respect to this prediction. But here, I mean, what we want to, this is, we need to ask if this is the uncertainty that we want to report, or what is the interpretation of this kind of percent that we have here. So the idea that I want to show you in this talk is that in principle, rather than compute the uncertainties, we also need to interpret these uncertainties or this kind of insecure of the network that has respect to the predicted value. So here, this the next slide, I want to show you that basically sometimes this value that we get from the softmax is not that we want to looking for because this corresponds to the output of the softmax, which are computed by using the maximal likelihood estimation or the maximal posterior estimation. These are only point estimates. Only point estimates, and therefore maybe this is not the uncertainty that we want to report, because we want to report the insecurity that the network has with respect to this prediction. So here in this example, I show you, in this slide, I show you a couple of examples in which maybe we can now debate about what would be the interpretation of this 99.7%. So here in the top, I show you an example in which I use the same classifier that I used before, but this time I pass through the different image, and each image are rotated 20 degrees, and I pass through the image to the classifier, and I get the accuracy. So first, I pass the first image, which corresponds to the rotation angle equal to 0, and you can observe that the accuracy is around 100%, which is basically this 99.7%. Then I pass the second image, which is rotated 20 degrees, and I obtain the same result. And after 40 degrees, I obtain the same result. But when I pass through the image, which is rotated with angles larger than 60 degrees, you can observe that now the machine is predicted the number 2. So the machine says that, okay, this is the number 2 that you can see here. And not surprisingly is that the accuracy is the 19, is almost 100%. So it's like, so the machine here, we see that predict the wrong value with respect to this image, but he is sure that this is the value. And after we can observe that for 80 degrees, then the prediction is the number 7, and after 150, that is number 5, and only after angles larger than 160, again we recover that this is the number 1. And below, now this is another common example, which is the adversarial example, in which again, in the left panel, I show you the classifier, which predicts that is the number 1, and also with its probability. And then what I did is add some kind of noise. So you see in the right panel the same image, but maybe it's quite different because in the background contains some kind of noise. But you see that it's the number 1. However, when you pass through the classifier, this image to the classifier, you observe that the classifier predicts that this is the number 6, and the accuracy or the probability is around 90%. So in this case, in this kind of examples allow us to think that maybe this is not this kind of probability that comes from the softmax. This is not the way the kind of maybe uncertainty that we want to report. Maybe we would like to report something more robust, which tells to the which try to such that the machine try to say that I don't know. Right? So this is basically that you try to find some kind of uncertainty which measure the robustness of the network and tells to the machine, or try to such that the machine can know what is not known for it. So now in this, so for in order to overcome this kind of problems and find this the variance uncertainty, actually in the literature of machine learning you can find these two types of uncertainties. One is called the epistemic uncertainty, and the other is the aleatoric uncertainty. So the aleatoric uncertainty is some kind of uncertainty that you cannot reduce in deep learning. It's something that is intrinsic to the data. So in this plot, I show you a couple of examples. Here in the left part, you see the data set, which is spread, contains a high variance. So in this case, you expect that the aleatoric uncertainty must be high. While in the right part, you observe here this kind of data set in which this data contained small variance, and therefore you expect that the aleatoric uncertainty must be low. So in this case, it means that the machine, when try to fit this data, for low uncertainty, maybe is more confident about find out the best model, which fits or which explains your data. While in for high accuracy, for high aleatory uncertainty, maybe the model is not confident about this prediction. So this is one way to report that how confident is the machine with respect to these predictions. And the other uncertainty that I want to talk is the epistemic uncertainty, which is some kind of uncertainty that you can reduce. So in this plot, I show you examples of epistemic uncertainty. So you can observe in the leftmost part of the plot and the rightmost that there is not any data. So in principle, the model is not robust enough in order to extrapolate the predictions, and therefore the uncertainty is big. So the uncertainty in the region is shown in this blue region. So you can observe that in regions in which you don't have any data, the model seems to be unconfident about the probable predictions. So the way to reduce this kind of uncertainty is just add some data. In this case, you add more information, and then the model has more information to get more confident predictions or more confident results.
Hector, can I stop you for 1 second?
Yeah, sure.
Just to try to improve the sound a little bit. Are you using the sound from your PC or from your headset?
From the PC.
Can you switch to the headset, you think?
Okay.
Should be in the options of Zoom.
Yes.
In the little arrow next to the mic, you probably have two options.
Can you hear me well, better?
We can still hear you, but I don't think that it's, I think it's the same microphone. Do you see the icon for the mic in the Zoom application?
Yes.
Next to it, there is a little arrow. Probably very next to it, just between the mic and the camera icons.
Okay. Yes. Exactly.
And there you can switch mic, maybe.
Yeah, exactly. So I put this option. I don't know if it's better.
I don't know. It's
yeah.
Okay. If it doesn't work out, maybe just to try to use your mouse farther from your laptop so we don't hear the sound of the mouse. But okay, go on because.
Yeah, so yeah, because there is only two options. Switch the option, but.
Okay, just go on. It's fine.
Okay, sorry for this. Okay, so this is the two uncertainties that we manage usually in machine and deep learning. So in this slide, I show you a diagram. You can observe this diagram was taken from this paper. It's a very interesting paper in which explain briefly each method that people use for obtaining uncertainties from deep machine and deep learning methods. So in this diagram, you can see the classification of the different types of methodologies that we can use in order to get uncertainties. And these methods are classified depending if you are using stochastic neural networks or maybe deterministic ones, and also what kind of uncertainty you plan to report if you want to interpret these kind of uncertainties from the frequency way or the Bayesian way. So in this Bayes way. So in this talk, I want to explain a little bit more about the Bayesian neural networks, and maybe at the end, I just want to show you just one slide about the Gaussian process. Okay, so now let's move on to the Bayesian neural networks. So let me first explain the traditional neural network that you can see here in the subplot A. So this the deterministic neural network is just that you have the input layer, the output layer, and between you have the interlayer. You have the neurons, which are in the layer, and there are some connections, and you see that these connections that is usually called the weights are just fixed numbers. These fixed numbers, as I said before, are training via the maximization estimation, like maximization likelihood estimation, or you add some kind of regularizers, you optimize these values via the maximal posterior estimation. Now, from the Bayesian neural networks, the idea is try to get this kind of uncertainty that I mentioned before, which corresponds to the uncertainty with respect to the parameter in the neural network. In this case, what we need to do is try to average our different models of the neural network, and it's for the reason that we need some kind of stochastic in the network. So in this case, in the Bayesian neural network, instead of having fixed numbers, we have distribution functions, distributions. So the weights here are sampled from this kind of distributions. Now, in the Bayesian neural network, we need to explicitly propose the distribution in the weights, but also we can do implicit. So we don't need we don't need to define the prior distribution in the weights, but there are some methods in which you don't need to do that. It's completely implicit. And these methods are below in the subplot C and D, which is a dropout and drop connect. So dropout was a technique which was proposed for regularization, and in 2015, some people proposed that this dropout, if you took out the dropout during training and also during test, also can get you can also provide uncertainties from this kind of models. And this dropout basically is a mask from the Bernoulli mask that you have in the network, and depending on some kind of probability, you can drop some neurons. So each time that you pass through the image, basically you have a stochastic network in which drop some neurons and keep on the others. While drop connect, you don't drop the neurons, but you drop the weights itself, the connections. But I mean, I worked in this with this model, and also there are some papers which report the performance of also report the performance of the connect. And basically, I got the same result, which is very bad models for reporting uncertainties. Okay. Now I want to show you some mathematical description behind of the neural networks. So let's assume like the data set, which corresponds to the pair of coded features and targets. And the idea is try to optimize the parameters such that the machine can learn the map between the features and the layers. Now, since I said before, we need to add some kind of distribution of the weights. So in this case, we define the likelihood, which is the probability of the output of the network given the input and given the W, which are the weights. This likelihood, for instance, for regression, we can assume that is the normal distribution, because of the normal distribution of its classification corresponds to the distribution associated with the cross entropy function. Now, the posterior distribution of these weights can be obtained using the Bayes law that you can observe here. And finally, if you want to predict you can predict the target for a new instance, which I call the X star, then you can use this formula. So basically, you have the probability of this of the target of this new instance is equal to this expression that is commonly used for doing inference. Okay, so for computing this integral, you can, for instance, use Monte Carlo. But the problem with the neural networks is that most of the neural networks contains thousands or millions of weights. So in this case, this problem of computing this integral using Monte Carlo is intractable. So we need to propose an alternative methods for solving this kind of integral, for solving this integral. So one of these methods is called the variational inference. So the idea of variational inference is that since we cannot compute analytically this posterior distribution over the weights, then we propose an approximate distribution, which I call here Q, which depends, of course, of the weights, but also depends on is parameterized with some with this theta. So, for instance, if I assume I approximate the posterior here in a Gaussian distribution, theta is the means and is the variance. Okay, so since we want to approximate this Q, the posterior through this distribution Q, the idea is that Q is as close as possible to the posterior. So the way to know how close are those distributions, we can use divergence. So variational inference is common to use the callback label divergence KLL, and this divergence is given by this expression that you can see here. So the idea here is like to minimize the KLL such that that we know that we have a good approximation of the distribution. So here the idea is try to minimize KLL with respect to the parameters theta. Okay, so since we need to compute this integral, so now we want to minimize this integral. The problem is that, of course, we don't know the posterior of the weight. So in this case, what I did, we are going to do is take this expression from the Bayes law and substitute plug in here in this integral, and after doing some maths, we get that this KLL can be expressed via the evidence lower bound, the elbow, which is described by this expression that you can see here. So the minimization of the TLL now is transformed into the maximization of the elbow, like the formula that you can observe here. So this elbow contains two parts, two terms. One of these is this part that you can see that this is the expectation of the likelihood with respect to the approximate distribution. So in this case, maximize the likelihood means that try to find a model which explains better the data. Minus, then we need to minimize this TLL, but this TLL now is between the approximate posterior that we propose and the prior that we include in the weights. And so after maximize this elbow, we get the better parameters theta, which such that Q Q is close to the posterior. So after that, after obtaining this theta stuff, which maximize the elbow, then we just plug in into this formula, into the inference, and at the end we get the new inference expression, which allow us to get the new prediction value with respect to a new, the predict value with respect to a new instance. Okay. Now, since we have now the predictions, we can now compute the variance. So in this case, we just use the definition of the covariance matrix for this prediction. Sometimes this covariance is diagonal. It means that you don't expect a correlation between between the parameters of the output. And in this case, you can just do again some maths, and at the end you can split this covariance into terms. So we can get in the first term, which is which corresponds to the aleatoric uncertainty, while the other which corresponds to the epistemic uncertainty. So here for the first expression is basically just the dispersion with respect to the different outputs that you get. So you have the stochastic network and you pass the same image different times, and the dispersion of this data basically gives you the aleatoric part. While here in the second term, you observe that is the dispersion, but with the parameters of the network. So basically here now you see how aleatoric is your network, and in this case you can get, or you can obtain basically the uncertainty related to the weight, so to the parameters of the network, which corresponds we saw previously to the epistemic uncertainty. And from this formula, we can see we can create some estimators, which you can observe here, and basically you have this expression. So in case in which we write the Bayesian neural network here in the output like a mean and like a sigma, so we can get the aleatoric and the epistemic part, just like the aleatoric, just the average over the sigma, so the covariance matrix of the variance obtained or predicted by the network. And the epistemic is the standard deviation of the variance of the means. Okay, now how we can train this network. So how we can incorporate the prior or the approximate posterior. So in this case, there are some proposals. One of these very useful is called the mean Gaussian field, in which you approximate the approximate posterior like a normal distribution, and you assume that the weights are independent. So in this case, this approximate posterior is the product of the Gaussians for all the weights. And the prior for the weights is just, again, since are independent, you can propose a Gaussian distribution, which means 0 and the deviation 1. So if you assume that the prior and this approximate posterior is given by this form, you can find an analytical formula for the QLL for this step. So in principle, if you assume that these conditions, you get an analytical function here for this step. And for update the parameters for the distribution, in this case we can use an algorithm which is called the reparameterization trick. This is because since we are sampling from this distribution, we cannot apply derivation, so we cannot apply the gradient descent for update the value for the new parameters of the distribution. So in this case, we need to use another alternative. So these reparameterization tricks, what it does is that you take the distribution and or these the weights are sampled from this. I mean, the distribution can be rewritten in a deterministic function. So you can basically split the distribution into parts, one which is deterministic and the other which is aleatoric. This is not for all the distribution. For Gaussian distribution, we can do that, and some other distribution, but not for all distributions. So for the Gaussian distribution, basically what you have is that the weights are sampled via two parameters, which are mu and sigma, which are deterministic functions. So since they are deterministic functions, in this case, we can use the usual backpropagation algorithm that we use in deep learning in the traditional deep learning for update the parameters. So in this case, we observe that for these Bayesian neural networks, now they double the number of the parameters of the network. And after update, we take the sigma and we just multiply with this epsilon, which represents the stochastic part that we discussed previously, where epsilon is just a sample from the normal distribution. So this is the way that you use in order to update the parameters in the distribution of the weights. And so now this method, which is really good for update the parameters in the distribution. This distribution contains, or this parameterization contains a high variance. So in order to avoid or in order to reduce this high variance, there are some methods like a local parameterization trick and also the flip out. So the flip out is just that you take the mini batch, which in which you update the parameters of the distribution, and then you multiply with a random matrix which contains elements 1 and -1, and basically you try to get independent realization for any mini batch. So in this case, you can reduce the variance of the estimation. And again, as I said before, there are other methods in which you don't need to explicitly define the prior or the posterior. So like dropout or batch normalization methods contain implicitly this kind of prior or posterior. So you don't need to explicit this distribution of the weights. Okay, so now some properties of the variational inference, of the variational inference method. So since this approximate distribution, in this case, what we did is just transform the inference, which was integration problem, into optimization problem. So in this case, we have some nice properties like, for instance, we know that we reach the convergence instead of, for instance, MC methods in which we don't know exactly if when the method or the model converge. And also one of the advantages of this method is that it's quite fast to get the inference results. So in this case, is very good for machine learning or big data, in which we have a lot of data and we need to get the inference quickly. So in this case, variational inference is a good method for carrying out this task. The problem for this model is that since we are assuming assuming a specific distribution for approximate the real posterior, in this case we introduce a bias. And also this bias also incorporates bad calibration methods. In other words, the prediction or the uncertainties predicted by the model are not well calibrated, so we cannot reliable about this uncertainty. So we need to calibrate after these uncertainties. Now, there is also ways to maybe overcome these kind of problems. And one of them is try to modify the QLL that we observe here. So instead of working with the QLL, we can work with another kind of divergence. So here I show you one of them, which is the alpha divergence, in which is a family of divergence. So here alpha represents a parameter you can change. For instance, for alpha equal to 0, you recover the QLL. And then for other values, you can get another kind of divergence. So here I want to show you one of the problems maybe that they provide bad calibration in this variational inference. So in this case, I show you the target. Suppose that we have a target value with a bimodal distribution that you can observe here, and then we want to use the different divergence, so different parameters of alpha, and you get the results when we are assuming that the approximate posterior is a Gaussian. So for alpha equal to 0, which corresponds to the QLL, or for negative values of alpha, you observe that the Gaussian try to fit to the lower mass of the distribution function, and this is because this kind of divergence are exclusive. So in principle, try to put the distribution in places in which there are where there are not much mass into the real target distribution. So in order to maybe to get a more realistic or more reliable approximations, maybe we can tune this parameter alpha, and you can observe, for instance, for alpha positive, that these values try to cover the total distribution. So here for alpha 0.5, you can observe like the midpoint in which you get inclusion distribution or inclusion divergence or exclusive divergence. Okay, so now for this mathematical discussion, now I want to show you some applications. One of them corresponds to the 21 centimeters. So here I show you one of the equations that we use in order to find or to detect the 21 centimeter signal, and this is a relative, this is the brightness temperature with respect to the CMB, and you observe that this brightness temperature depends on different parameters. One of them are cosmological, like omega n, so corresponds to the cosmological size, and others corresponds to the astrophysical part. So here the task was try to generate some maps of the 21 centimeters, and from this maps try to train the network in order to estimate such that the network can predict the parameters associated with these maps. So here I use the 21 centimeter fast for creating these maps, and I evaluate 4 parameters, which corresponds both this omega n and sigma I, which corresponds to the from the cosmological part, and these other which corresponds to the astrophysical part. And also I create different maps varying these 4 parameters, and also I created these maps in the range of the redshift between 6 and 12. Now, so in this case, after that, I propose to a method for estimate better the parameters of this map. So in this case, I create I stack all this image. So this corresponds here. This is an image in which you can observe that I stack the image with the same parameters but at different redshifts. So basically here we have an image which each channel corresponds to a different value in the redshift. And then I did a neural network. Here I use the BGG16 architecture, and at the output I create the news and the sigma, which mu corresponds to the value of the parameters, and the sigma gives the variance of these parameters and the correlation that maybe these parameters will have. And then at the end, what I also propose is add the normalizing flows. This normalizing flows, basically what actually does is try to modify this normal distribution and transform into a better complex function. So in this case, we will have a robust likelihood that could explain better of data. Then the metrics that I use in order to assess the performance of the network are the R2, which corresponds to how precise are our predictions of the cosmological parameters, but also, as I mentioned before, I need to take into account the reliability of the uncertainty. So in this case, I need to determine how well calibrated is our network. So in this case, what I did was try to compute the confidence interval, which basically corresponds to or is defined that the values of the predicted values. If I define the percent of the confidence intervals, I expect that this same percent all the true values falls in this interval. So, for instance, if I create a confidence interval of the 68.3%, I expect that this same percent of the two values falls in these intervals, and also for 1 sigma, 2 sigma, 2 sigma, etc. Okay, so in this case now, for the calibration, I use two methods. One is try to tune some hyperparameters in order to get the best calibrated network, or the other method is that just train the network, and after doing test, I calibrate the network. So these are the two methods, and in the second methods, I also include the normalizing flows in order to check if maybe the normalizing flows improve not only the predictions of the cosmological parameters, but also provide a well calibrated network. So the results are shown here in this table, in this slide, sorry. So for this table, you can observe the R squared for all these parameters, and this EF and MAF corresponds to the different methods for normalizing flows. And you can observe, for instance, for the EF, that you can obtain well calibrated, reliable uncertainties, well calibrated network. Here also I show you this triangular plots in which I also report the correlation between the different parameters predicted by the network. And here in this table are the dot sigma constraints for the parameters from this model. Another thing that I observe here is that for calibrating the neural networks, the best thing that we can do is just train the network and try to tune the hyperparameters in order to get the best the best value of R squared without and don't care about the calibration. And after obtaining the best model, then we start to retrain this model. So actually, after training, what actually do is freeze all the layers, and we just keep the last layer for retraining again. But in this case, we apply the normalizing flows. And these normalizing flows, what actually does is try to improve this likelihood. And at the end, we get reliable uncertainty estimates. And also what we saw is that also the negative or the R squared is also a little bit increased. So this is one of the main results in this work. Now, this is another example. Is now instead of using the 21 centimeters maps, we use the CMB maps. So we use the same methodology. So we use, in this case, the class code. So the class code, we create the power spectrum for different set of cosmological parameters, and then we use help to create these maps. And from these maps, we take the center patch for 20 by 20 degrees, and this is the maps that we include into the network. Again, we work with channels in which one channel corresponds to the map of the CMP temperature, and the other corresponds to the polarization in order to determine if the network can predict or can estimate the cosmological parameters for this channel. So they try to verify if we can include different observations in the channels, and to see if the network can combine all these experiments in order to get reliable, or in order to get high precision of the cosmological parameters values. So in this case, we did the same task. So here you observe the correlations of the cosmological parameters predicted by these neural networks. But this time now we want to what we wanted to do is try to compare with MCMC methods. So here in this plot, you can observe the results given by the Bayesian neural networks, and also the results reported by MCMC. So by the MCMC is just like we use Koala software in which you take the power spectrum and you obtain the parameter, the parameter, the cosmological parameters. And we just compare. So here we can observe that the MCMC is more accurate with respect to these predictions. But in this table, you can also observe in the runtime, for instance, that if we spent 4 hours for estimate the cosmological parameters for the MCMC, for variational inference, it takes only 10 seconds. So here we have a very huge difference of runtime. So instead of while variational inference provide wrong accuracy estimates of the cosmological parameters, is quite fast. While the MCMC is the opposite, you can get high accuracy, but take more time for obtaining the results. But here also I show you another proposal, which is what's happened if we can combine both methods. So in this case, I first of all I train the variational inference, and then I compute the parameter estimations, or the distribution, or the posterior distribution of the parameters, and then this distribution of these results are put in the bottom of the MCMC techniques. So in this case, the variational inference provide initialization for the MCMC, so a good parameter space in which the MCMC must be sampled. And in this case, we observe that the runtime for obtaining the result from MCMC are notably reduced. So first, for instance, we use only MCMC. We got the results in the convergence of the MCMC was reached in 4 hours. While if we add this variational inference, it takes only 2 hours. So we reduce by half the time of convergence in the MCMC. So this is also variational inference. Also, we can here we prove that we can combine these two inference techniques in order to get the result of these two works. Okay. Here I will also show you another kind of an alternative way for doing obtaining calibrations, well-calibrated networks. So in this case, you can observe the different methods that we can use in Bayesian neural networks. And here I compute the coercion probability. So as I said before, the confidence interval must be equal to the coercion probability in order to get an unbiased and a good estimator for the uncertainties. So you expect to get a straight line. So for the different methods, different hyperparameter tuning, you can get overestimation or underestimation of this uncertainty. So what you need to do is try to tune these upper parameters in order to provide this straight line, which allows you a reliable uncertainty estimates. So here I use again the different the alpha divergence. So in this case I show you the area which corresponds to the area that you can find between the plot that you get for the coercion probability with respect to a well-calibrated network. So here, for instance, for the red plot, the area will be all this part, right? And I just plot here. So for tuning the different values of alpha, you can observe that for alpha equal to 1, which corresponds to just switch the distribution in the definition to the KLL, you get well-calibrated networks. Yeah, you can observe here. And most important, as I said before, is that if you train and you tune, I mean, during training, you start to tune these hyperparameters, you get this curve. But if you train first and then you start to calibrate it, so after the training, so you get this part. So the takeaway message here is that it's better to train first in order to get the high performance, for instance, the high or the minimal mean square error or the high R square, and after calibrated the network. And here also you can observe the negative loss likelihood for different values on alpha, and you observe that this is the trained, the baseline model here. And when you start to train to calibrate after training, you get lower values for the negative likelihood. And here are the different methods that I propose for tuning, for calibrating the network. So again, you just freeze all the network except the last one. And then in the last one, you have the means and the sigma. So you start to train, you can freeze maybe the sigma, and you start only retrain based on only the values of the output of the mu, and you can get this well-calibrated network. Or you can also retrain again the mu and the sigma, and you get the different results here. And here also you can observe the R squared, which is quite I mean, it's approximately constant, but even you can observe here that the R squared decreases a little bit for positive values. So here, for instance, it's just a trade-off that you have. So you have better performance in the likelihood for larger values or for positive values of alpha, but in this case, you reduce the R squared. So in other words, you get well-calibrated networks for alpha values, but you start to reduce a little bit your R squared. And also for negative values of alpha, you get higher R squared values, so it gives you a good precision in your parameters, but you get bad estimations in the uncertainty. So it's just a trade-off that we need to take into account when we want to tune these hyperparameters. And finally, I just a preliminary result that I want to show you. This is another way to provide this kind of uncertainty. This using Gaussian processes. So in this in this plot, it's just a preliminary result, but this just I want to show you this plot in the sense that this is another because I mean Gaussian process is another way for estimate these kinds of uncertainties. And here I show you the data for F sigma A with respect to the redshift. And here I want to compare the results by these Gaussian processes in which you can observe here are the points, and here is the mean of the mean of predicted by the Gaussian processes, and the level of 1 sigma uncertainty is given or described by this plot in blue. While for the Bayesian neural networks, I compute the aleatoric and the epistemic. So the aleatoric, you can observe this magenta, the magenta color and 1 sigma, and you observe that indeed the aleatoric uncertainty increase when in places in which you observe high accuracy, high dispersion of the data, in which is here in the redshift around 0.2, and in places in which you can observe less dispersion, the aleatoric uncertainty is lower. But in the epistemic, in which is this red plot, red line you can see in the background here, you observe that this is small here, the epistemic, because you have more data, but it starts to increase when you start to move to high redshift because you have a lot of data. So in this case, you have this uncertainty in which tells you that you need more data here in order to get a better prediction in your results. Okay, and here I show you also the parameter estimations of the sigma 8 and omega matrix using these formulas. So in this case, I obtained that for Gaussian processes you can get small uncertainty estimates. So the difference here between Gaussian processes and the general networks is that the Gaussian processes gives you the uncertainty, the total uncertainty, the sum of these two uncertainties, while in the general networks you can split, you can compute by separate the aleatoric and the epistemic. Now the question will be if we need to split this kind of uncertainties. So I can say that maybe it depends on the task that you want to do. For instance, if you want to create emulators using these anybody simulations, we know that these anybody simulations are very expensive, and in this case we have only a few boxes, for instance, of few data sets. So maybe it's very important to take into account the epistemic uncertainty in order to see if we have, if we need to add more data in order to decrease this uncertainty, or is enough? Is just enough, and we need to improve the quality of the data. So it depends of the data that you want to do, that we need to split this, or we can to get by separate the aleatoric and the epistemic uncertainty. Okay, so I arrived to the end of this talk. So in conclusion, so I show you the Bayesian neural networks as one of the common methods for obtaining uncertainties in this in deep learning, and also I motivate the inclusion of these neural networks in order to try to get additional information which tell us how confident is the prediction reported by the neural network. And also, I also show you that we can also combine in SimC and variational inference in order to get a more robust inference method, which combine the accuracy of SimC and the speed of the variational inference. And also, we can do the opposite. We can also use the variational inference. We can use the variational inference, and maybe we can provide more robust priors in the weights, and we can, and since we cannot now compute analytically QLL, we can use different MCMC techniques in order to maybe get better precision, or better values reported for the variational inference. So that's all. Thank you very much.
Okay, thank you, Hector. So do we have some questions? You can either raise your hand or speak directly. I, for one, have several questions. So I will start with the first one. I think I possibly missed a key link in your in your explanation. Could you go back to the slide where you show the network architecture?
Yes.
Yes, this one. So at the end of the network, you predict mu is average value of parameters and sigma is variance. Is that true?
Yes. So, for instance, in this case, I need to estimate 4 parameters, right? Which corresponds to these parameters. So in this case, the mu
this network, it is a Bayesian network, or?
Yeah, yes, this is a Bayesian neural network.
That maybe that's where there is something I did not understand. I thought that if you had indeed distributions for the weights, you would just make a number when trying to predict the result for a given sample.
Yes.
You would just pass it several times through the network. And from the output of the value of the parameter, you would get an average value and a variance.
Yes. So,
but it seems like it doesn't work that way.
Yeah, here it's just that in the output, I just expect a distribution of this network. So that's why. So in this case, for instance, you can get a Bayesian network in which the output is you get distribution, and from the distribution you just sample. But in this case, I want to, I mean, here in the output, you get it's just the final distribution, what you expect to be. I mean, because here this is the likelihood that I expect, which is Gaussian. So in this case, here you build a Gaussian distribution, which you have the means, which given by these parameters, and the sigma, which corresponds to is the covariance matrix, corresponds to these parameters. And then you start to minimize with respect to the negative log likelihood.
It's just does that mean that if you pass several times a given sample, you will get different value of mu for a parameter?
Yes, exactly. Yes. So yes, exactly. So this is the idea of the Bayesian neural network. So here I take this image. For instance, suppose that this is the image in a test set. So I need to pass through 2,000 times or 1,000 times the same image in order to get in order to recover the epistemic uncertainty. So each time that I pass through the image, I get different results.
Okay, but that
I cannot pass only just one time the image and take from this distribution all the samples. I need to pass through different times because I need to move through all the weights.
Okay, but what you say is that when you pass it several times, you recover the epistemic uncertainty.
Exactly.
And what you think, what is that the idea that when if there is some aleatory uncertainty, you will quantify it by the way you specified the result with a sigma and a mu?
In principle, the aleatoric is given by when you have after passing different times the image, you get different values for the sigma. So in this case, I show you here that when you average all when you average all the results correspond to the sigma, you get the aleatoric. Because in principle here this corresponds to so here each time that you pass the image, so the model have a different I mean, perception of of the spread of the image. So in this case, it's close in the sigma. for the reason that when you average, you get this aleatory, you get the dispersion of the data. This is that we want to get from the aleatory.
And just to be sure, in your case, you could probably have two types of aleatory uncertainties. You could pass the image with the same cosmological and astrophysical parameters.
Exactly.
But you could have generated different density fields for your 21 cm fast code that would give you different pictures for the same parameters. That could be one type of aleatory uncertainty. Another type would be if you included instrumental noise in the images.
Yes.
Did you include both type? Meaning, did you include instrumental noise, and did you generate different density field for your learning sample?
Yes. So I don't think I did include instrumental noise. So this is something that I expected to do later. That yes, this is something that is really important. So in order to get a more realistic image, so this is something that I expect to do later. And with the other, yeah. So in principle, I just generate a different image with the same cosmological parameters. And then I just start to change. So I have these images with this range of the parameters, and I created with the same set of parameters different images
Okay.
in order to get this randomness in the
okay.
Yes, in the image.
Yes, Norma, do you have a question?
Yes, thank you. Thank you, Javier. First point I would like you said in one of your results that variational inference. I mean, this method is much more faster than Monte Carlo when compared with Monte Carlo. I would like to know, is that for, I mean, how, I mean, you gain how much in time, but I mean, that is all, which are the constraints you need to put in your data set? I mean, for the size or for the type, I mean, is there, besides the time you gain, which is, I recognize is very good. Besides that, what do you gain?
This,
I mean, at the analysis of signals, and I mean, perhaps connected with that. I mean, and have you much more information again in the parameter estimation and gain in the signals you get?
no, this is, I mean, when I did this variational, I mean, this comparison between the MCMC and variational inference, I tried to look for first, I mean, how, I mean, the time that we spent for each method, and also how accuracy we get from both methods. So in this case, you can observe here in this table that the constraints are very tight for MCMC. But also the other thing that I want to find was that if I provide good correlations between the two parameters. So in this case, you can observe that I listed, I mean, if you compare the correlations between the two parameters, you get the similar results. So in principle, you don't get additional information from variational inference and SimC. So basically, from the, I mean, for interpret the physics behind of this of the data and the parameters, you get the same information. So here I think that the issue is how accurate you get the estimation using different methods, and maybe also address the problem of instances in which takes a lot of time to get the results. But in principle, you get the same information.
But yes, but then you can is good. I mean, to for if you have really high, very huge, large data sets.
Yeah, yes. Yeah,
that really that is crucial in some sense. I mean, it's
yes, exactly. Yeah, exactly. So this is the motivation for variational inference, that in principle, if you have a big, large data set, big dimensionality, you get the result
yes,
faster.
To combine different data sets. I mean, to enlarge. So, and the other point, I mean, I'm sorry, I just finished. The other point is, I mean, how about if do you want to track, to really know, to analyze non-Gaussian processes? I mean, non-Gaussian, I mean, that you believe that it could be some non-Gaussian signals, some non-Gaussian signature. Have you applied or are you planning to apply to that? I mean, in general, what you have, I mean.
Yes, for, you say for no-Gaussian, for extracting no-Gaussianities, right?
Yes, even if these are very small and so no, and what is known, but it's interesting to know in these approaches what you can do.
Yes, so in this case, I use for working with no-Gaussianities, I use this 21 centimeters, and also I use this Quixote dataset for estimating the cosmological parameters for designing model simulations. And the idea here was it's for the reason that the motivation for including the normalizing flows, because here in the likelihood you expect, I mean, you assume that here I propose that this is Gaussian. Now the inclusion of normalizing flows, maybe you can get more flexible distribution. So in this case, the normalizing flows try to explain so you have this kind of non-Gaussianities, maybe these normalizing flows adjust in order to explain better the data.
I see.
So yeah, so this is the motivation for including the normalizing flows. But in general, I mean, you can from this kind of networks, you also can get this non-Gaussianity. So because inside here you have a highly nonlinear application function, so maybe this so the idea is that you can extract this non-Gaussian information.
But it will take, of course, much more. I mean, you will need much.
No,
I finished.
We have other questions.
To point out, yes, that is for Javier. Just let him know that Javier, your mouth perhaps make a friction that is amplified with a microphone. I don't know, but it came to us all the time. The noise of your mouth. Of your mouth. It's a pity because
yes, sorry.
So try to pay attention. Thank you.
Okay, so I think we have another question by Soteris Lukatos.
Just yeah, very nice seminar. Thanks. Just the first reference you gave, which was an introduction by someone, I did not write this down, where you said it is an interesting general introduction for likelihood. Can you show that that reference in the first or second slide? Yeah, that was before. The one with the branches. The branches just after, I think. After the one with different cases.
Ah, okay.
Yeah.
Yes,
Holemeister or something, but I did not write this down. No, it's a reference by someone else.
Yes, here, yeah, this is I mean, this is an example. So
No, Hector
yeah.
is asking for the slide where you showed, this tree with different cases.
The tree, yes, sorry.
Uh,
It's a preprint by, yeah, here, this one.
This one. Sorry, yeah.
Huller-Meyer. Okay. Thank you very much.
Okay.
Thank you very much. It is. I saw your papers, but I also wanted to check this one. Thank you.
Yeah. Yes.
I have another one for you, Hector. So you mentioned that the training of the BNN takes about, you said 10 seconds compared to the 4 hours with the MCMC.
Yes.
For
inference, exactly.
Yes. Oh, for inference. But how much time does it take to train the network?
No, it takes in this case only 20 minutes or something. Yeah. Okay. The problem is, the problem. Yeah, you're right, because the problem is that sometimes also you need to tune the hyperparameters, so you need to spend more time for obtaining a well network.
But one question that I wondered really about is that how does compare the number of iteration that MCMC did for the inference and the number in the learning sample that you used for training the network? Because you see, that's very important in the sense that sometimes just computing the model is the bottleneck. The time for computing the model, it can be the bottleneck. And if it is the bottleneck, and if MCMC needs many more forward computation of the model, then what you need for training your network, then it's interesting to do the inference with the network. So do you have any idea about that number in your case?
No. I mean, can you replace because I can understand.
So you have this model that when you do the MCMC, you just you take your parameters, you compute your signal, and compare it to your targets, and then do it again and again and again, and typically do it maybe 100,000 times.
Yes.
And then on the other hand, with your network, when you train it, you have your learning sample that you built using also a model to which you would give the parameters, and that would create the corresponding signal.
Yes.
And so you have a number of sample in your training sample. And how many is that?
Okay. Yeah, so yeah, you're right. So it's relative, no? Because from MCMC, using the COAJA, basically for each step, you need to call, for instance, the class code. In this case, it takes, I don't know how much it takes, for maybe 6 seconds, something, for obtaining the theoretical value. And then, I mean, compute the likelihood and start to do the iterations. While here for variational inference, I mean, also maybe you have maybe I don't remember, maybe a couple of minutes for each for each epoch.
Yeah, but okay. But that's the time for the training. I'm not even talking about the time of the training. I'm talking about building your learning sample. How many cases did you have in your learning sample? Because you see, you get a big uncertainty, but possibly.
No, actually, yes, I use the same parameter space in both.
But the same sampling of the parameter space.
Well,
I mean, was the sampling as dense for your learning set as what MCMC did when it was trying to find the posterior distribution for the parameter? Because typically that's what I have in mind, is that possibly MCMC would do a very fine sampling when trying to sample the posterior.
Exactly.
And when you build your sample to train the network, maybe you do a much coarser sampling of the parameter space.
Yeah, so in this case, I mean, I use from the range of the parameter space, for instance, for creating the image for training the network, I use a range in the parameter space, which is uniform. I mean, I have the maximum and minimum, the values for each parameter, and I start to sample, I mean, to create 60,000 or 50,000 images in the range. For the MCMC, I use the same range, but I put the Gaussian distribution, assuming a specific value of the cosmological parameter. So this is what actually do using this Monty Python or Coage. So in this case now, I don't know how we can compare maybe.
Okay.
I mean yes.
Okay, then
the parameter space in which each method sample.
Okay, maybe we can keep discussing
Yes.
that later on. Does someone else have one more question? Maybe. If not, no. So if not, maybe we will stop here and thank the speaker for this very nice talk.
Okay, thank you very much. I'm sorry for the maybe the sound. But,
that's fine. We will be in contact with you in a few days. Okay.
In a few days. Okay. Okay. Thank you very much.
Okay. See you.
Bye bye.
Adiós.